problems, I think.
So, this is the point. Everybody can give a problem, but the idea is to make it a little bit different. Okay, so far the seminar is going well. The conferences, GADEPs conferences are going well. So each time I'm thinking to add more stuff to this GADEPs activity. And at some point, it is already 1 year that I'm thinking to create a list of problems. But the point is that everybody has his own problem. But if you have a problem that which you can pay for the solution, then the issue becomes different. So as I said, I think starting from my own problem, the idea is that to create a list of problems. I think I would say problems that not so much philosophical, like this Grothendieck's period conjecture and so on, so difficult. At the end, you have some idea that it can be solved. I would say if a PhD student think about that problem, at least produce his PhD thesis, even so he doesn't solve the problem. I think the good problem is the one that your brain starts working. And I think let's say in the next 10 or 20 years, if this project is successful, at the end maybe one publish this list of problems in a book and so on. But I'm not sure it is going to be a success, or it will be, my problem will be the first and the last problem. But let's see.
But the problem is to find a list of problems?
No. No, the problem is to find a list of people who are able to pay their problem, the money. What? Anyway, the form solving the problem, of course. There is some, let's say, as I said, really what I'm thinking maybe at some point in a kind of make a list and to put in a book. And in order to make them serious, the owner, the one who proposes, then he had to associate some like a kind of money. Let's just put, and the price, okay, yeah, it is better, it is more. Yeah, but you can say some package of cookies. It is not, and the idea is that at the end, let's say, I have to say, to make a kind of people who knows the problem and the kind of scientific committee who can write a report and so on. And I talked with Emre a little bit. Roberto is more a specialist in the problem that I am talking. But anyway, let's start by announcing the problem. And as I said, when in the next GADEPs conferences, I will try to see if it is possible to add more to this. Okay. But anyway, let me go to I will just try to announce it, and the way it is worse that in my case I think I was first thinking of this one, but I thought it is too cheap, so let's just take R. It is becoming more expensive, but especially if you put R. And when the time passes, it becomes cheaper and cheaper. But it is just a dollar sign, not really.
Even though the dollar sign is the
What? Oh, well, the American economy is going to go very bad. Well, I don't know. Anyway, let me announce the problem and the reason why at some point I decided really to start with this problem. Yeah, we can. Well, okay, let's go to the problem, and after that, everybody goes to Praia Vermelha to enjoy the scene. Okay, so you already see U and D, the parameters, but I will go to my notation T. I do it with N and D. And parameter space of smooth hypersurfaces. So this is basically then homogeneous polynomials in x0, xn plus 1, degree D part, and then you cut out the singular hypersurfaces. And I think, for example, before all this stuff that we heard in this conference, the main examples were of just for hypersurfaces, especially the period, the name period, and so on at the end comes from the periods of either the elliptic curve or abelian integrals in this context. So it is historically it's also important. So this example of Hodge locus, even so I have not defined Hodge locus, it is already mentioned, hypersurfaces containing, so let me try to write down, I will write, let's say, T in T, then the corresponding hypersurface is xt, which is given by the homogeneous polynomial ft equal to 0. And this basically T are the coefficients of the monomials for me. Containing, so n will be even because I am this, not the general context of the Hodge locus of Greg, but just the Hodge cycles and the corresponding Hodge locus. So, so n even, and containing some linear.
It's not fixed.
Huh?
Not a fixed plane, but any plane.
Any plane. This is the any plane. Well, if you know the definition of the Hodge locus in that context, it's still, Roberto mentioned, it's still a kind of amount of work to show that really this is a component of the Hodge locus, if you know what is the Hodge locus. But anyway, this is a reducible subvariety of T. This one is already mentioned. Codimension of T check inside T. It is n half plus d minus n half plus 1. This one. So if it was a generic, since the codimension is high and it is much bigger than also the dimension of T, well, we're not a small n and d. If this variety was a negative generic, it must be smooth, but actually it's not smooth. So this guy intersects itself a lot. Maybe I try to make a picture. Actually, this picture, maybe, well, I wanted to make a two-dimensional picture in the three-dimensional picture in the two-dimensional blackboard, but let's just make this just this picture. So anyway, it intersects, and it also intersects a lot of in different ways. So this is our T check. Well, in one intersection point, let's say, I will do the Hodge locus in the local context, whatever Georgia and Roberto were saying. So in particular, let's just take a point in the intersection, and then my world will be just in the neighborhood of this point. So I will take intersection. For example, one typical intersection point of this loci is that when it has 2p, you take a hypersurfaces, and it has two such, let's say it was a linear cycle, and one linear cycle, when you go along this one of the linear cycles disappears, the other one survives, and when you go in this direction, and the other way around. So let me go call this one. So this is check V p n half one, and let's say this one, and this then p and half check. But actually, you will see that it doesn't. This intersection of t check by itself, it has to do also that you have to fix n half. This one, it's also a projective space. So you have to fix this m also. So for m fixed, this guy will intersect itself. Let's call t check space of hyper surfaces x with 2 p and half check, and also intersecting in PM, and M is fixed. So this means that this guy, the other intersection points, the M is different, and so on.
So V and half is like the space of all, and there is
No, what I'm saying that these two things are this. This is just a local branch of this global variety. And then I want to forget this global variety T check. Or you may take in this way. What is this? These two things. You take hypersurfaces with these two guys. One deformation in X together with this guy will produce one let's say analytic variety, and deformation of X together, the other linear cycle will produce the other branch. Okay, so, and if you want, I mean, at the end of the easiest case are the case of surfaces, let's say n equal to 2. I'm talking about hypersurfaces containing 2p1. Either these 2p1 do not intersect, or they intersect in one point. In this case, let's say I have to say m minus 1 until n half minus 1. So p minus 1 means empty set. So this means that these two projective spaces do not intersect. Okay. So far, so good. I'm already near to the announcement. Okay, so let's return back to my original point. So I will try to talk about this deformation. I have to fix a point, or for the computation I have chosen a theorem. So let's just put a 0, meaning that I have fixed the point. And then maybe it would be better to do in this way also. Okay, maybe I don't do it because I am now defining the set. But what I'm saying, from now on, I will use x0 for a fixed one, and then I will try to talk about the deformation of these things, because I want to introduce the notion of the Hodge locus in this context. Okay, so let's. I will consider this algebraic cycle, this Hodge cycle. So our integer, our natural number, because I do, and this, our check can be negative. Anyway, it doesn't matter. Our check not equal to 0. And at the end of the day, everything that I will tell will depend on this rational number, r divided by r check. But I want to write in homology. So this, at some point, I will start writing everything in homology. But let's use the classical notation. X0 intersected with hn xz. Okay, so, well, I got two algebraic cycles. I have this Hodge, let's say, this Hodge cycle. And, okay, so as it was mentioned, I mean, there was the concept of monodromy. So the thing is that topologically there is no, so if you, sorry, actually this was, so let me call this one delta 0. So delta 0 Hn x0 z. So there is the monodromy, parallel transport, and I will not do global monodromy, whatever Greg was doing. It is just local monodromy, because as I said, my Hodge locus will be just a local object. So for any t in a small neighborhood of your marked variety, you will have this cycle. Or, well, I am you like homology, but let's just okay. Let's do it this way. Okay. Now, what I'm saying that I will not go away from 0, just a little bit move from 0. Not global monodromy. I have to go turn around the discriminant, return back. I have to get.
X0 singular.
No, x0 is smooth. I never consider.
I'm saying if you don't move very far, then you don't go around somebody that's singular.
Yeah, but then what I'm doing that I have to say. When you want to define the monodromy group, first you have to define it locally. What is the transport of one cycle, the cycle from one fiber to another one? No, yeah. You don't suddenly go along a path, turn around the discriminant, and return back.
You're not gonna, you just want to
Parallel transport or flat section of the Gauss-Manning connection or whatever which language you like it.
not
Yeah. Okay. Yeah.
You're not getting an automorphism.
No. As I said, I'm not using the monodromy group. Maybe I make the very simple picture. Okay, so this is my big T which might have produced monodromy. I have just in 0. I take T here. If this is my variety, this is delta 0, of course. And this is just, let's say, the parallel delta T, that's all. I mean, this is where the monodromy is, I have to say, where our things period started. Families of elliptic curve, families of Riemann surfaces, and then all these topological cycles you can transport to the nearby varieties. Okay, so okay, so I think my notation for so let's do this one. I have to put now 0, 0, 0 here. So my yeah, okay. So that's so the Hodge locus. As I did, I'm not doing the global aspect. This is just a local. It's just so delta t. It's always you exist, but it's not necessarily Hodge. So this is the first naive definition of the Hodge locus. T in a neighborhood of 0. Such that delta is Hodge. And what does this mean? That delta t, it is h and half xt intersected with hn xt z. It's always here, but not necessarily here. And well, it was already mentioned. This is by definition, it's not clear, but it is really analytic variety, and actually it is more. It has a scheme, analytic space, or analytic scheme structure, and so on. This, in a minute, I will tell you. And okay, maybe. So since I don't want to use global notation, I'm just in a neighborhood of a smooth variety. Maybe I tell also, maybe I write also this one, Vz, a branch of T check check. So T check check was parameterizing two linear cycle. So in a not rigorous way, I write it parameterizing deformations of x0 together with p and half. I think if I use the language of Hilbert scheme is better, but anyway, I want just little intuitionally. So you have here x together with two linear cycle. When you go in this direction, then one of the linear cycle disappears. When you go in this direction, the other one disappears. But once you stay in this, this is not actually also point, it is a loci itself. And in this loci, the two linear cycles are there, and they do not disappear. And of course, if you go, suddenly x goes deform it very generically, all the linear both of our linear cycle will disappear. Okay, so yeah, exactly. This is the point. No, but this intersection is a topological. This means that at the end, if you, in the origin, you have fixed that this is PM, and if you deform it a little bit, again, the deform, and still you have these two guys, this M will not change. Because the intersection of the homology class of this one has a formula in terms of M. And this is a topological, so the M is. But anyway, let's. Okay. So let. I have to do something else. Okay, maybe. So this is the point. That you already know that this Vz is inside V0 check. Now, because maybe I can again. Because this is when you have a Vz0, both algebraic cycles are there. At the end, they will solve the Hodge conjecture for you. And if you have the delta, what I'm saying, if you take here, t here, this t, they come together with xt, p and half, t, p and half, t check, and so on. And then you will, at the end of the day, your delta t is just again arch p and half t arch check. Well, let's see. Okay, so maybe I put the number again here. And I will tell you why really I think it is important. As I said, all of us, when we are trying to solve problems, we produce also thousands of problems. so Vz, this one is, even you don't just consider as a variety, not really as a scheme, because I have not told the scheme structure, is smooth of dimension one bigger than dimension of this guy. And just remember that this guy is depends on this rational number R and R check. Maybe I make the picture here. So to each rational, Oh, okay. Oh, okay. D equals to 3. M equals, okay. I'm not making a good copy paste of what I've written here. So this case. And n bigger than 6. Cubic hypersurface. The intersection must be n half minus 3. For example, if it are cubic fourfold, the 2p2, they do not intersect. So they have talking about 2p2 in a cubic hypersurface which do not have an intersection. And I have cut out the cubic hypersurface because the conjecture here is a kind of trivial in the case of cubic hypersurface. But if you want to, since the cubic hypersurface is well studied, what I'm saying, this situation corresponds to 2p2 in a cubic hypersurface not intersecting each other.
So you want D not equal to 3?
Huh?
You want D not equal to 3?
No, it equal to the cubic.
You only want it for cubics.
For cubic hypersurface, yeah, exactly.
Not the cubic four.
Not the cubic 4. Yeah. Then it starts from the dimension 6. Well, if I have to. So the idea is that maybe I repeat my picture here. This is V P n half. This is V. Huh?
It's important that why isn't m equals m?
I will skip this part because all this work that I did with Roberto and also a lot of computation in my book, it says that in other cases we don't get interesting Hodge cycles. So the idea is that I want to, so when the dimension is bigger, this means that I get some Hodge cycle. In other cases, one doesn't get interesting Hodge cycle.
This has to hold for every R and R.
Yeah, exactly, in this. And actually, you will get, the idea is that you will get a pencil infinite number of the components of the Hodge locus passing through at the point f you have started. So let's say, this is the point. I didn't insert R and R check in my notation, but actually this depends on, so for each rational number, you will get infinite number of the components of the Hodge locus, and they cross the point that I have started. But of course, because of this dimension issue, they are much bigger. They are not inside this strata. And they are one dimension bigger. And actually, one can compute the tangent space. This is the tangent space. If you take RR check two different rational numbers, let's say the corresponding tangent space will be different, and you can see that you will get infinite number of components of the Hodge loci. And in a minute, I will write the dimensions, dimensions. But for example, I have to say. Yeah, okay, well, my notation always fix the things in the base and where it started, so let's say, yeah, exactly. Yeah, but no, everything that I am writing at the notation depends on the notations of the point I started. I start from x0, p and half 0, and so on. But at the end, there are these are analytic varieties in the neighborhood of this point in the parameter space. Okay.
Is there a reason for that they really, those key analogies really are switched under?
Yeah, for example, I made it in this way because, for example, if you go along this one and you do globally and return back from one p and half, you get the other p and half.
Oh, you know that. That's
Yeah, this is easy. I mean, this is because my T-check variety is irreducible, no? So this means that if I have a Fermat variety with a lot of these things, you can do a kind of global monodromy, and one p and half turns in the other one. Yeah, exactly. There are infinite.
But how do you, that we know that the Hodge locus here, by what Greg said, is algebraic, right? So there's only accumulates along
No, this is this Hodge locus. Its components are algebraic. The whole Hodge locus is not algebraic.
Oh, no, that's like, the whole Hodge locus is algebraic. But the maximum one could contain all of them, right?
Yeah, exactly. So the question is, what's the
No, my understanding from Greg that he considers the special, this positive, which he claims that there are finite number of them.
Yeah, but it's not positive, just means everything apart from points. Yeah.
Yeah.
But it's like Cattani and Kaplan, some each component. All theories about positive dimension. Cattani and Kaplan, they don't care about the points.
Yeah, but for example, in the case of surfaces, there is, for example, this.
Wait, hold on, that. That's not they don't care about points back, because I know.
No, okay.
I know that the first thing they proved was actually about points. Because Cattani and Kaplan, I know because Greg wrote to this Cattani and Kaplan. The first thing they proved is in the case where the base is dimension 0. And then it's just like a finiteness statement about like the number of points.
Yeah.
So they do, Cattani and Kaplan definitely. Yeah.
And the Cattani-Deligne Kaplan theorem, if you remember, if you fix the intersection number, the self-intersection of the Hodge cycle, then you will get, let's say, the algebraic. But the point is that if you fix the self-intersection of the...
No, but like the theorem that Greg explains, like you, without fixing the intersection, the maximum components of the Hodge locus, they are finite here. Like if you restrict to the positive dimension.
Well, he's dealing with the Mumford-Tate group, so it's like different, right? The Mumford-Tate group will have more places where it like, I mean, they could get smaller even if there's no Hodge, even if this particular class is not Hodge, some other class.
No, anyway, I think...
But I think it is true that they would all have to be contained in one bigger, since you have infinitely many of those, there'd have to be some, what do you call it?
maybe just...
Some special thing that contains all of them.
So, by the way, for example, in the case of this Noether-Lefschetz loci, Voisin's work, there are infinite number of Noether-Lefschetz loci, which are much below the codimension, huh? Yeah, but anyway, we can discuss. But here, my impression was that in degree, the cubic hypersurfaces. But anyway, let's discuss this one.
But there's no contradiction.
Huh?
There's no contradiction.
Yeah, yeah.
No, it's just gonna be a bigger one, just different from the whole space. The question, what is this bigger one? I mean,
Yeah, so maybe it would be a better idea, good idea to make a conjecture about the dimension of that thing.
Yeah.
Yeah, exactly.
Second bigger.
Okay, then it would have to be maybe at least dimension of VZ naught plus 2.
Yeah, that was my question.
Like that. Maybe let me write down the codimension here.
Yeah.
Oh, what time is it now? Okay, so well, I think I am trying to write. There is one version in the archive, the 3-page. I'm trying to write down the more evidence and so on. Okay. Either the conjecture is very easy. So let me say some the kind of again philosophical word. Since the idea was that I wanted to construct more interesting Hodge cycle for hypersurfaces. So if the Hodge conjecture is true, and this conjecture is easy, let's say, let me in this way. Ah. Yeah, yeah.
Like, do you want,
Yeah, I will write it. I will write it. In a minute, I will write. So I think it can be that the conjecture is easy. But if I believe the Hodge conjecture, this means that you will solve the, so maybe I have to come, in the new version, I am putting more, let's say, verify the Hodge conjecture for this, let's say, for this delta t in Vz, which is not in, well, it's a Vz, but anyway. In this way, I think you can start trying to write down equations of the algebraic cycles, and in a minute I will.
This last sentence, is this part of the conjecture that needs to be proven? Or
Yeah, after I was scared that maybe the first part it's too easy. Then I added this one also to make it more difficult. But anyway, actually, if really the conjecture is easy, this means that you will construct the algebraic cycle, I think. This means that you will write down, play with equations and so on, and you will be able to verify the conjecture and the Hodge conjecture, both of them. But the idea is that the other. Okay, maybe I want to do exactly this thing of Patrick. So if it is easy, this means that then you will play with polynomials and construct algebraic cycles. Maybe one example that I can say, Aoki Shioda, in order to prove the Hodge conjecture for Fermat variety, they did, as Shioda did it with these linear cycles, but at the end of the day, they realized this very simple equality, very high school equality, and I just want to explain the easiness. Where it is? Zeta 3 plus zeta 2 z times x plus zeta 3 2 y plus. So what I'm saying, Aoki Shioda were able to prove the Hodge conjecture for Fermat variety for more cases, and the whole of their idea started from just this equality. They saw that there is this kind of decomposition of this combination of monomials, and then they introduced more algebraic cycles in the Fermat variety, and they were able to prove the Hodge conjecture for more cases of the Fermat variety. And what I am saying, if really the conjecture is true and the Hodge conjecture also is true for delta t, at the end you will play with, you will start from Fermat, trying to find more algebraic cycle on Fermat and so on. But yeah, the conjecture is based on, but the evidences all comes from the computation from. So the idea is that if near the Fermat it is bigger, your Hodge locus, by continuation it will be bigger everywhere. Because this, let's say if you take, let's say, this T check, you can prove that it is irreducible and so on.
So if you prove the equality at one smooth point, you're done. If it's irreducible, then you don't.
I think it is just one point, and one hypersurface, it is enough. And especially this dimension issue, you have to do just in one point. Even in the Fermat will be enough.
But surely it's not smooth every point.
Maybe let me say. Okay, then maybe but at least in the case in the Fermat, this T check crosses itself a lot, but the branches themselves they are smooth, and yeah, maybe I have to be careful about this one because there must be very weird hypersurfaces. No, okay. Well, I think I have to a little bit. Maybe let's say let's for the moment put the x0 Fermat, and in this case, because the computations come from here, and then I will try to see if really I can claim it for. I think I can claim it for any hypersurface, but let's x0 Fermat. But anyway, the main idea is that around arbitrary hypersurfaces, that this one is. Dimension is bigger than this one, even the thing is singular, will be kept, no? because this guy is irreducible, and you are claiming that this is contained in a bigger space. They survive. V bracket Z is the one that just the Hodge cycle, corresponding Hodge cycle survives. Okay, maybe. Well, there are.
But if I could choose R to be 0, I think.
No, I am for this reason. I have taken R0 out. I put.
R hat was not 0, but R is.
No, R hat is not 0. R was a natural number. That's why.
Natural numbers don't.
Because otherwise you will get.
My natural numbers contain 0.
No, my natural is N0, not that.
No, but as an example, R could be 0, then.
Yeah, if R0, it is just the Hodge locus are these branches. Yeah. If one of the R0, then so for example, you will get these two branches, which has lower codimension, and then suddenly for R check non-zero, you will get this other branch of the Hodge locus. Okay, maybe just well, I will just say two. So first say this one. So if you put, let's say in this range of codimension where these things are, the lowest codimension is this one. This is achieved by codimension of let's say this T check. This is the lowest codimension. The biggest codimension is this Hodge number. In this case, it is 3k minus 1, 2k plus 1. For a sudden, I change my notation just to write down. And codimension of this Vz, it is, maybe I write 1, 6, k to the 3 plus 3, 2, k to the 2 minus 40. Plus 4, and then I write plus 1, because plus 4 is the Vz dimension, and plus 1 is this, let's say plus 5. And, That k and half. So the lowest codimension is this one. And this codimension, as a function of k, it grows like 1/6 k to the 3. And it is the same growth as the lowest codimension. And it is far away from the, let's say, this 2k plus 1.
That's given your conjecture, because your conjecture is what the codimension is.
Well, what I'm saying that at the end, the dimension of this Vz, I know it is 4, plus 4. And I'm just comparing that its growth is like the minimal codimension, not really near to the highest code.
This is assuming your conjecture.
Huh?
You're saying you know that your conjecture is about the codimension, the dimension.
No, in this case, I'm just comparing this 1/6k3 with 1/6k3 here, saying that it is the codimension is very low.
So you have equal.
Huh?
You said the codiment would be bracket C equals something, but that's not this conjecture.
No, once again, Francois? What?
I'm just repeating what Patrick said, but isn't the conjecture to compute this codimension?
Okay, well, I mean, the conjecture is that this one is exactly this one, but the codimension of the VZ I know. So this part until here, it is the codimension of VZ. But this is easy. This is just a, I have to say, counting the number of parameters and so on, because this guy parameterizes algebraic object.
Assuming the conjecture. In assuming your conjecture, the codimension of V bracket Z is that?
Assuming the conjecture, the V bracket C is this one. This plus 1. Yeah.
Right, that's the conjecture. And then if you assume it's smooth, does it prove the conjecture? If you prove that it's smooth at a point, does it actually prove the conjecture?
If you prove that it is smooth as an analytic scheme, that it is. Because for the moment I formulated it just analytic variety. But if you consider its ideal which it gives you, when you compute, for example, just tangent space, you see that it is bigger than really the underlying variety. It might be.
But it's only bigger by 1.
Yeah, it is bigger by 1.
But doesn't that show that it, like Roberto was just saying, either the dimension has to be equal to dimension of VZ, or it has to be equal to dimension of VZ plus 1?
Once again, what?
Either the dimension of V bracket Z has to be equal to dimension of VZ, or it has to be equal to dimension of VZ plus 1.
Y-E, no,
It's bigger than the dimension of VZ, bigger equal.
bigger than equal, yeah.
You compute the tangent space of the possibly non-reduced scheme, and you find the dimension is plus 1.
But it doesn't, well, let me say, something that I asked Roberto to do. That maybe I write here. T0. What I'm saying?
I think that you mean that the n plus 5 is the codimension of VC, right? I mean, you claim that the V of C brackets is bigger, right? So the codimension is smaller.
Oh, okay, I am, okay. Sorry. It's the minus one I have to make. Okay, I am talking, okay. I write it, sorry. You are talking about this thing, huh? Oh, sorry.
So it's plus 4 or plus 5?
So this plus 4 is this is for sure. This is the dimension of the VZ itself.
Dimension or codimension?
The codimension. Well, when I am alone, I think, yeah. VZ is smooth, yeah.
I don't understand though. So then you know the local equations for V bracket Z, and you know that would say that the tangent space is the dimension of V plus 1. So wouldn't it just seems to me, I could be wrong about this, that it's either the dimension
I have made it.
have to be V. I should get $10,000.
You are already. Okay.
But it would be a non-reduced thing of just VZ. Oh, okay. Okay.
I have one idea. There are two options for that. Either it's equal to VZ.
Either it's equal to VZ as a variety, but it has some stupid scheme structure that just comes from this Hodge theorem, and they don't repeat with the more normal scheme, usual, or same scheme structure, or
But anyway, what I'm saying, computing tangent space, verifying the conjecture in the level of tangent space is not enough. This one can, by Artinian-Goranstein things, one can prove it. Actually, I did it by computer for many cases. Roberto could do it for.
It's unclear what left side, what you computed really for left side. I mean, because you
Okay, this is 0, then x0 Fermat. Okay, well, in the written version, you will find that.
no, it's just that you defined V bracket Z as a set, and therefore automatically it defines the
Okay, now here, this will be analytic scheme.
It's the set of, I mean, it was written down as the set of hypersurfaces where the same is
No,
on.
that's the other V set. V set is the set.
Without, no, with the brackets.
So V bracket Z, it is completely unclear what it is. You just have theoretical definition, but you don't have really have to say if I pick a hypersurface, you cannot even decide if it is in V bracket Z or. Yeah, but the tangent space doesn't mean, as I said, this has a scheme structure.
No, look, you wrote down, I have a photo of this, you wrote down, it's the set of parameters where delta t is Hodge.
Yeah, okay.
So therefore it's automatically defines a reduced variety. I mean, if you write it like
This was the set theoretical definition, but now we are going, for this equality, we are using the scheme structure. So,
exactly, that's what I said.
so here, for this reason, so that one I wrote because I wanted to write the dimension. I don't care about the scheme structure. But here, in order to compute tangent space, the only data that I have from a V bracket check, it's defining ideal. Not really, and defining ideal might not be reduced and so on. So for this one, for this statement, you have to return back to this scheme structure of the thing. But for the announcement, the conjecture, as I wrote, you don't need really to say that to talk about the scheme structure, because I'm saying that as analytic variety is bigger, just one dimension bigger.
Yeah, like what Roberto just said, the conjecture reduces to whether it's smooth or not, given what you guys already know.
What?
The conjecture, the way you're saying a conjecture is like, the conjecture is that V bracket Z is smooth.
Of bigger dimension, one bigger dimension.
No, you already know that. You already know this Roberto's result, right?
Yeah, exactly. Yeah, exactly. So it is smoothness, just a smoothness. Okay.
We have to all see added.
So the point that then I have to rewrite the announcement as a scheme. So if it is smooth and then the tangent space is one dimension bigger, then it will be automatically one dimension bigger as variety. So I think at the end of the day, the moral of the story is that you have this VZ, and we are claiming that there is something bigger component, and actually a pencil of these guys. I don't know how to make a picture. Just let's say crossing this VZ, and they will produce a different Hodge cycle. But I think the time is finished. Well,
When you say pencil, you mean for every rational number?
this is the point. This pencil depends on just rational numbers.
Right.
It's not a usual pencil depending on continuous parameter. And but anyway, something this is infinite number of components of the Hodge locus, much below the. And I think maybe I have to say also so the tangent space is the first approximation. For the higher approximation of these things, there is no cohomology theory involved. For example, Griffiths, they did all this infinitesimal variation Hodge structure to handle all these tangent spaces and so on. But for higher approximation, I had to just forget all this cohomology theory, write down the equations of this Hodge loci as formal power series to truncate them and so on. And but anyway, I think in 2 weeks I will write down the new version of the text, writing all the evidences why this might be true. Maybe I write some commentary regarding this Greg's stuff and so on. Okay.
First of all, the smoothness. It's just look the other. If we could take R equals 0, just for example, you don't have smoothness because you have branches.
Oh no, I'm taking local branches. It is not the global. So this means that it is not as smooth at Fermat. But since I am taking a branch responsible for the deformation space of hypersurface, well, let the surface together with one line. this local branch itself is smooth. But of course, globally, it's intersect itself.
Now, I think, again, you need to be clear because probably the set theoretic locus is going to be smooth, but you want the analytical scheme that you have in your mind, what you have written down, you want us to prove that that is smooth.
Yeah, but in the announcement, I didn't want it because I don't really say that what is the scheme structure of that guy.
No, I think it's probably trivially true that the reduced thing is the branch has to be smooth. Yes, the branch has to be smooth. This is like
Yeah, but I put also the second condition that it is the dimension is bigger. If it is smooth and the dimension is bigger than VZ, then it is something non-trivial. If it is the same, it is V bracket Z is the same as VZ, okay, the smoothness is there. But the idea is that it is smooth as one dimension bigger. Okay, sorry for I made a lot of confusion with the dimension and codimension.
In the case where n equals 4, it's trivial because of global duality or something?
Yeah, exactly. Maybe I think the n equal to, so maybe this is, maybe I tell this one.
Is there like a geometric description of the cycle?
This is also another very interesting question. There is no, for example, this P2, and another P2 does not, which they're not. So for cubic, d equal to 3, n equal to 4. So very simple Hodge theoretical argument will give that all the Hodge loci codimension 1. This means that at the end you have automatically the first part of the conjecture. But since the Hodge conjecture is known for cubic fourfolds, then you say that the conjecture for N4 is already proved, but not proved effectively. And in the same way, one of the things that I always say, Lefschetz 1-1 theorem is true, but it is not proved effectively. This means that there is no method, there is no proof of Lefschetz 1-1 theorem, which says that, okay, if I give you a Hodge cycle, let's say Hodge cycle, you construct explicitly the curve for me. In the same way, for example, in this case also, as I said, the conjecture is true, but it passes through the proof of the Hodge conjecture for cubic fourfold.
And the fact that there's no effective thing for n equals 4 means that it's probably very hard to prove the second part, the HC part. On some abstract ground.
Well, I don't know. If somebody claims that he has proved the Hodge conjecture for all cubic n-folds without proving my conjecture, I would be very unhappy because it will not construct for me the algebraic cycle. So all these, anyway, I think it is. So I think, huh?
So you want an explicit representative of the cycle, or just prove somehow that it's like?
So this is still, as I said, I'm slowly announcing. I would personally, I would be happy that if you constructed cycles, algebraic cycles. For example, we are. Patrick was talking about verification of Hodge conjecture for this abelian variety, but at the end they do not construct any cycle. Even so, it crosses through non-algebraic world to get some saying that such thing exists. But anyway, I think I have to pay. If somebody claims that the Hodge conjecture for all cubic n-folds is true without constructing cycles.
Can you say again, why did you have this condition on the dimension of intersection of the two? You said it wasn't interesting unless, it's not interesting unless Pn over 2 intersects Pn over 2 checked.
This is the point. In my book, Hodge theory book, I started really, what was the objective? I wanted to produce more and more Hodge cycles for hypersurface. I'm not interested at all Hodge conjecture. I want to have explicit example of a Hodge cycle. And the only source was Shioda's work for Fermat variety. Apart from Fermat variety, computing periods is, periods are in general transcendental numbers. Finding Hodge cycles is extremely difficult. So the idea was that I start from Fermat, where I have Shioda's work, I can compute Hodge cycles and so on, and I try to start deform the Hodge cycle. And to see if I get some non-trivial Hodge cycle, such that my deformation of my original algebraic cycles is not enough to verification of the Hodge conjecture. And in this way, to get more and more Hodge cycles, and as I was putting, it is maybe now I have more courage to say, I think if it is not the easy conjecture, it's a counterexample to the Hodge conjecture. And the reason I think all these things that in very low codimension, constructing algebraic cycle must be easy, even you can write down equations. And this guy, this Hodge cycle, the codimension of Hodge is very low. There was this results of Voisin. In the case of surfaces, there was this, if you remember these two numbers in George's locus. In the case of surfaces, the lowest codimension is this one, this parameterized hypersurface, surfaces containing a line, surfaces containing a. So the idea is that in lower codimension, really you can write down also equation for your algebraic cycles. And so for this reason, it might be easy. If it is easy, you can write the equation of algebraic cycle, really. But if it is really hard, this means that you are going to more to I would say, something that it might be a counterexample. Yeah, this delta t.
So I propose we thank Hossein